Yeah, so we were talking about integral test. Said, okay, if you start with some series, doesn't matter what that is, okay? When we convert this over to an integral, where what we've done is we've taken this function, right, of the natural numbers, and we've converted it to a function of x. We take a look at that integral and see if it converges or diverges, and then whatever this does, that does, right? But there were three conditions that we had to have for this test to be able to be used. We had to have that this function here is what? Continuous.
Greater than 0.
Positive or greater than 0, and decreasing. So you must show those three things. Usually it's easy to show it's continuous. Sometimes it's a little troublesome to show that it's positive, but I think it's, for the problem I gave you, is pretty obvious. Decreasing, to show it's decreasing, you either have to take the derivative and show it's negative, or you have to show that the sequence decreases. So I'm going to move on, all right? I only did one example in class. I gave you a quiz, so we're just going to move on. The integral test is good, but it's not like the big test, right? We actually do have a test here that's going to be very, very nice. It won't solve all our problems, but it's going to be the one we use a lot when we move forward in this chapter. So the next type of series that we want to look at is p-series. Right, in the integral test, have y'all by now printed out the series test? You should have that with you from this point. Yeah, that table. You can see the integral test on there. So now we're going to talk about p-series. So p-series is a really simple series to figure out what it does. It's 1 over n to the p. 1 over n to the p. So the p there, you could look at the p as standing for like power, right? And so just, I don't know, someone give me a p. Any p, 6. Okay, so if p is 6, then this series looks like this. N equals 1 to infinity, 1 over n to the 6th, right? So if we start writing this out, this equals, well, we plug in n equals 1 first, we get 1 over 1 to the 6th, plus then 1 over 2 to the 6th, plus 1 over 3 to the 6th, plus 1 over 4 to the 6th, plus dot, 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 forever, right? Now the question is, does this series converge or diverge? Please recognize this is not a geometric series, right? The n here is not in the exponent, the n is in the base. If you have the quiz, please turn it in. Okay. The n is in the base, not the exponent, so it's not a geometric series. It's a p-series. Now, the question is, does this converge or diverge? So if we do a quick nth term test, right, the first test we learned, the pregnancy test, if we look at this right here, right, take the limit of that as n goes to infinity, and that goes to 0, right, which means the test fails. And then we have all these different tests we can do. The way you can do this is with the integral test. I'm not going to show it, but you could do this. Imagine I go through the steps, right? You would basically set up this integral from 1 to infinity of 1 over x to the 6th dx. And this is easy to do. Easy, relatively easy to do, because this is just a power of x. We could use a power rule, and we could show that this actually converges, all right? That this converges. So we could do that for any power, couldn't we? For any power, I could just do this, do the integral test, do this, do the integral test. So instead of going through and showing all that, we just have a result, an end result, all right? And that's going to be right here. So there it is. So there's a p-series. P-series has that form, 1 over n to the p, right? So what happens? What does this p-series do? Well, if the p right here, if that power is greater than 1, then this is going to converge. And if the p is less than or equal to 1, it will diverge. Hey, what is it if p is 1? If p is 1, what is this? 1 over n. What type of series is 1 over n? Drum roll. It's rational, but it's a special one. 1 over n. Constant over, so it's harmonic. Okay? So if p is 1, this is harmonic, and all harmonic series diverge, right? So you could actually look at the harmonic series as an example of the P series. All right, so anyone else want to turn in? Quiz? Okay, thank you. All right, so done? Can we proceed? Y'all trust that we could do the integral test and that it would work out? Okay. So all P series, we can figure out what they do. All we have to do is look at what the power is. If the power is bigger than 1, it's going to converge. If the power is less than or equal to 1, it'll diverge. By the way, that power can be a decimal. It does not have to be a whole number. Okay, that P, I gave you the example P is 6, but you could use 6.2. You could use 0.5, any P you want. Okay, we move on. So we are now going to talk about this thing called the comparison test. And the comparison test is the first test that I think we're going to do where students really start to get confused as to how tests work, right? Like up to this point, the tests that we've been done have been pretty straightforward. Like the integral test, yeah, we have to check a few things, but then we just do an integral, right? The comparison test is tricky. And you can tell it's tricky just by the wording of it, all right? So let me show you what the test says. All right, we now look at this other test called the comparison test. I will first explain the test and the conclusions and then explain with animations. I may or may not do the animations, but okay, so this is the test. So let's say we're given this. We're given a series. If you have the quiz, I'll take it. Okay, so we're given this, and there's a condition on this test. There is a condition on this test that's really important, and that is this right here, okay, must be greater than 0. In other words, this will not work if we ever have a negative term anywhere in our series. This test will fail, all right? It only works for series that create positive terms. Now, it's okay. The next section, we have tests that handle when you have negatives. But this one right here only works when that's positive. Okay, so let's say we've got that. And if you think about it geometrically, remember a series is just the sum of a sequence, right? So if you were to take that a sub n and start just the a sub n, if you were to take that and start showing me, they would be dots, right? A bunch of dots, and then we're adding up all those, like the heights of the dots to get the series. So what if I told you this? What if I told you that this a sub n, when you put the dots here, you plug in 1, you get a dot. You plug in 2, you get a dot. You plug in 3, you get another dot, right? What we're doing when we're adding them up is we're taking, how tall is that, plus how tall is that, plus how tall is that. It's like the lengths of a bunch of little line segments, and we're adding them, right? What if I told you that this sequence of numbers right here was always smaller than some other sequence, all right? This sequence in blue, I'm going to call it B sub n instead of A sub n. The A sub n is the one in black, right? What if I told you that every blue dot was bigger than or equal to every red dot, okay? And I told you this, that this series converged. What do you think you could tell me? The other one also converges, right? Because what we're saying here is that if you were to add up all these blue dots, right? Add up the lengths of the blue dots. Add up all those lengths. I'm telling you it converges to a number. Well, your black dots are smaller than or equal, aren't they? So that sum should also be finite and should converge. Now, it doesn't necessarily converge to the same thing, but it still converges. Does that make sense to you geometrically? So I'm telling you that if we start with this, and then I tell you, and a sub n is less than or equal to some b sub n, all right? And that series with b sub n converges, then your conclusion is that your original series converges, right? And this is all on your table, all right? It's all there, but this is all there also, right? Does it make sense to you, though? You said yes. Yes? Okay. So why is this thing called the comparison test? The way the comparison test works is that we're going to start with a series where we don't know what it does. But we're going to look at it and we're going to say, you know what, that looks a lot like some other series that I do know what it does. And then we're going to compare the two. And if we can show that the other series we're comparing it to, those little sequence, that sequence is always bigger than this sequence, and we can show that the original, the thing we're comparing it to converges, then we don't have to do anything with this one. We can just conclude it converges. Make sense? Now, there's another possibility, okay? And that is, what if we start here, and what if I tell you that these blue dots are not always above, but I tell you they're always below? Okay? What if I tell you they're always below? Now, if the blue ones converge, can you tell me anything about the black ones? No, you can't tell me anything. Because just because the blue ones add up to be a finite number, if the black ones are taller than or bigger, then you can't tell me that the black ones add up to be a number, right? It could, but you can't guarantee it, right? But what if I now tell you that this diverges? So if I tell you that the sum of the blue ones becomes infinitely big, and your black ones are always bigger, then your sum has to become infinitely big as well, right? So there's two scenarios with the comparison test. The first scenario is this. If we're given this, and our sequence is always smaller than some other sequence, and that series of that sequence converges, then ours must converge. On the other hand, if the thing we're comparing it to, so this is kind of like an or, like we have another scenario here. Let me do it this way. Or we can look at it this way. We're given some series, right? Those are positive. And we're able to show that our a sub n's are always bigger than or equal to some b sub n's. And the series with the b sub n's diverges. I'm just going to put arrow goes to infinity, all right? If that goes to infinity, then our conclusion is what? Ours does, right? Ours does as well. Yeah, I should put diverges. Let's put diverges. It's more technically correct. Okay. So recap, we're given a series, right? We look at that series, we say, shit, I don't know what to do with it, but I think it kind of looks like this other series. And that other series that you are going to compare it to, you better know what it does. You hear me? Whatever, because you have to come up with the b sub n. You are going to be the one who has to do that. No one's going to give you any prompts, okay? You have to figure out what you want to compare it to. And whatever you compare it to, you better know what it does, because then you can draw a conclusion, right? So let's do an example, all right? Let's do our first example. First example we're going to do is my eyes are getting bad. Okay, the first example we're going to do is this one. So does this converge or diverge? Question. Sum. N equals 1 to infinity. 1 over 3 to the n plus n. All right, let's run through everything we've learned. So imagine when you're sitting at the final and I give you a series, I'm going to ask you if it converges or diverges. That's all you're going to have, right? So you're going to have to be able to run through all these different tests and know what to do, right? So the first thing I'm going to do is a quick nth term test, right? I'm not going to do it on the board because it's going to take too much time, but if I just take the inside, right, like this, right there, let n go to infinity, I get 0. So that test fails. Then I'm thinking, okay, geometric. Well, it's almost geometric, right? Wouldn't that be geometric? If I had just that, would that be geometric? Yes. I can write that as 1/3, right, to the n. Yes? And I would know what to do. But that's not geometric because it has a plus n. Can I split it into 2 fractions? No, because you can't do fractions that way, right? So you can't split it. So it's not geometric. What's the next thing? Harmonic? It's not harmonic, right? It's not linear, constant over linear. That's not linear, right? 3 to the n is not linear, so it's not harmonic. What else do we have? Integral test. Okay, maybe this will go with the integral test, but if it does, I have to be able to integrate what? I'd have to be able to integrate, I'd have to be able to do that, wouldn't I? No, thank you. I mean, maybe I could, but I don't feel like I'm going to enjoy that, okay? So do you see, like, what do? Right? We don't have anything. Well, we now have this comparison test. So if you think about n, right? Think about the n. The n is going to get bigger and bigger. We already know that this ratio goes to 0. That's fine. But what I want you to focus on is which of these 2 pieces down here has, I guess, more control over what's happening? Like what is having a bigger impact on things? 3 to the n or n? 3 to the n, right? If I let n get big, that 3 to the n really dominates the expression, doesn't it? That little n on the side, yes, it's getting bigger, but not as big as the 3 to the n is. So I'm thinking to myself, you know what? Like I said earlier, this really kind of does look geometric, doesn't it? So if I'm going to compare this to something, the geometric series would be the thing that seems reasonable to compare it to. So I'm going to, I should also point out, these are always positive, right? If I'm going to use a comparison test, these are always positive. So here I go. I'm going to do a comparison. Okay, so what am I going to compare it to? I'm going to try and compare it to this series right here. I'm going to try and compare it to that. So basically I'm imagining that n wasn't there. And then I'm just going to remember that that really means sum n equals 1 to infinity of 1/3 to the n. We talked about that last time, right? How that happens. Okay, now that is a geometric series, isn't it? Is it written the way that we like geometric series to be written? No, we like that to be an n minus 1, don't we? I could do that, couldn't I? But that's not important because all I need to know is whether or not this converges or diverges. So does it converge or diverge? What's r? What's the r? Remember, all geometric series are written a r to the n minus 1. Can you tell what the r would be here? 1/3, right? So even though I'm not going to transform this to make it look exactly geometric, I know that the r would be 1/3 when I do that. So this is geometric with r being 1/3, and that means it converges, right? Very important, right? Because what do we need for convergence? We need the absolute value of r to be less than 1. If the absolute value of r is less than 1, we get convergence. So what I'm going to do is I'm trying to figure out what this series does. I'm saying, hey, it looks a lot like this series, and that series is geometric, and it converges, right? Okay. So what do I need to do now to show that this one converges as well? What I need to do is show an inequality is true. Remember how we had the dots, the blue dots were either above or below our black dots? In this case, we want our blue dots to be where? Above, right? So this was our original series, right? And then this one right here, that we want our blue dots to be above, because if these blue dots add up to be a number, right, if they converge, our black dots are below ours should converge as well, right? So here's what I must show. I must now show that our sequence, right? Our sequence, this, is, how is it related to this sequence? It's less than or equal to this sequence. Okay, I must now show that that sequence must be smaller than this sequence, right? So that if you add those up, it should be smaller than adding up those. And I already know this adds up to be a number. So that must add up to be a number. So I must show this. That means I must show what? I must show that 1 over 3 to the n plus n is less than or equal to 1 over 3 to the n. I need to show that that's true. And I think it might be obvious right now that it's true, but I'm gonna do a cross multiply. When I cross multiply, why am I not worried about flipping the signs over? Because I know I'm not ever going to have a negative, right? 3 to the n plus n is never negative because n is going to be 1, 2, 3, 4. So that's true, right? I can do like cross multiply. Is that true? Yeah, you could subtract 3 to the n on both sides, couldn't you? Subtract 3 to the n. And you would get I think nobody would argue with this, right? I don't think. 0 is less than or equal to what? N? That's true because where does our n start? At 1. Okay, so that's true. So we're done. Check, right? I must show that this inequality holds, and I just did. Therefore, I can draw my conclusion. Therefore, the original series what? Converges. Now for this problem, now that I've gone through it, do you see, like, is it obvious, this choice that I made? Does it seem obvious to you? What if you would have tried something else? Like, what if you would have done it the other way? You would have said, hey, look, I'm going to ignore that, and I'm going to say that this looks a lot like 1 over n. Let's just see what would have happened, okay? Is that all right with y'all? Just to see what would have happened if you would have done that? So I'm going to run through a comparison here. Okay, the comparison I'm going to make is that instead of doing that, I want to compare it to 1 over n. Now, what do I know about this series? Because I said you better know what it does, right? It diverges, right? It diverges. Why? It's harmonic, or you could say it's a p-series with p being 1, right? Either way. Okay, so it diverges. All right, so if it diverges, then that means that when you add up all these numbers, right, you get infinity. So if our black dots are here, right, if that's us here, adding up all these dots, and we would want to have our blue dots where? Under them, right? Underneath, so that I know that if the blue dots add up to be infinite and the black dots are bigger, then ours, the black dots will add up to be infinity as well. So what must I show? Want to show. Want to show. I'm just going to put WTS, want to show. What do I want to show for this thing to work? That the A sub n is bigger than or equal to the B sub n, right? So I want to show that this is greater than or equal to this. And then you can cross multiply. And you get n is greater than or equal to 3 to the n plus n. And you can subtract n on both sides. Is that true? Is 3 to the n smaller than or equal to 0? No, right? No, this isn't true. Okay, so what can you say? Therefore, Yeah, what can you say? So this is an important idea of just logic, right? Our test said that we wanted to show that this was true, and we weren't able to show that that's true, right? We were comparing it to a divergent series. So what conclusion can we draw? Absolutely nothing. We can't conclude anything, all right? Nothing. We know nothing more than when we started the problem. When your inequality doesn't work out, it just means your comparison sucked. It wasn't good enough to show what you needed to show. What you can't do is say, oh, since this isn't true, that's not true, that must converge. No, you cannot do that. You have to find a series to compare it to where the inequality holds, and then you can draw a conclusion, all right? All right, so basically this failed, all right? Failed. But that wouldn't be the end of the world, right? Like, then I would just try a different comparison, and then maybe now I do the 1/3 to the end, and it would work, right? It would. All right, let's do another example. N cubed over n to the 4th minus 1. Notice something. Where does that series start?
2.
At 2. Do you see why? What if n was 1? The bottom would go to 0, so it'd be undefined. So starting out at 2, and we learned last class that, look, if you take a few numbers out of a sequence, it doesn't change the convergence or divergence. So it's okay to start at 2. All right, there we go. Does it converge or diverge? All right, so first thing I would do, nth term test, right? Can I stop calling it the pregnancy test now? Do you all know what I'm talking about when I say nth term test? Okay, so I look at that, take the limit, infinity over infinity, L'Hopital a few times, you're going to get 0, the test fails, all right? So that doesn't work. Is it geometric? No, you don't have n in an exponent. It's not geometric, okay? Is it harmonic? Is it constant over linear? No. Integral test. I could integrate that because if I imagine that's like x cubed over x to the 4th minus 1, I could see a u sub going there. I could see that possibility, right? Do I want to do the integral test? Not really, but I could maybe go down that road. See, so when you get to your final exam and you're doing these problems, right, like different students are going to do different things. And so one student might do an integral test and be able to show that it converged or diverged. Another student might do a comparison test. Another student might do something else, right? So when I'm grading, I have to actually figure out, like, did you actually show what you needed to show? Because it might work different ways. All right? It's not just one way to do it. All right, so where are we? It's not harmonic. P series, well, it's obviously not a P series, right? It's not like 1 over n to the P. What else? Is that it? That's all we have, right? Okay. Comparison. Any ideas of what to compare that to? Think about if n was huge. If n was huge, like, does that minus 1 really matter? When n is really big, does taking away 1 on the bottom really make a difference? Not when n is huge, right? So if you ignore that, what is that?
1 over n.
That's 1 over n. That seems like a decent candidate to compare it to, right? It seems like a decent candidate. So I'm going to try it, right? I'm going to try it. And we did this in the previous problem, right? When we had 3 to the n plus n, we said, which of those two dominates? The 3 to the n? We said, let's just kind of ignore the n. Then it looks like 1 over 3 to the n, which was geometric. So we're doing the same sort of logical thinking, right? So I'm going to compare. Comparison test here, okay? And what I'm going to compare it to is sum n equals 2 to infinity of 1 over n, right? Because when I ignore that 1, it's really n cubed over n to the 4th, right? And then they cancel out. You just get 1n on the bottom. That's why we're doing 1 over n. Okay, so I'm going to compare it to this. And I know that this is harmonic, right? Or P series, P being 1. And I know it diverges, right? All right, so if I'm going to compare it to something that's divergent, then I must show what? I want to show that this one is it less than, bigger, what? Bigger or smaller? The way I logically think about it is that all I know is that these things add up to be infinity, right? So I need these guys to also add up to be infinity, right? Which means these guys have to be small. So if I have a bucket of numbers, right? This is a bucket of numbers, and I'm telling you they add up to be infinity. And then over here I have a bucket of numbers, and if I tell you each of these numbers is smaller than those, can you tell me it adds up to be infinity?
Yeah.
If these are smaller than those. So those numbers add up to be infinity, right? These numbers are smaller than those.
Yeah.
Okay, so do you see a bucket of numbers over here? Positive numbers, yes? Do you see them?
Yeah.
Those add up to be infinity. These are smaller. In fact, I'm going to tell you what they are. They're all zeros. Will this add up to be infinity? Are they all smaller than those?
Isn't infinity an idea?
Yes, but it's that when I add these up, it just gets bigger and bigger and bigger and bigger, right? These numbers in this bucket just, you keep adding them up and the number just grows and grows and grows. If these numbers are smaller than those, you can't tell me that these add up to be infinity as well. Because if they're smaller, couldn't they all be zeros? Couldn't they? And they are smaller than those, and these are not going to add up to be infinity. Now, what if I tell you the numbers in this bucket are bigger than those?
Well, if the other one adds up to infinity, then the bucket with the bigger numbers is going to add up.
Exactly. So that's what the inequality is about. It's saying, okay, that bucket of numbers adds up to be infinity, right? We need this bucket to add up to be infinity as well, so the only way to do is to guarantee that the numbers in here are bigger than those. So I need these numbers in here to be bigger than or equal to the numbers in there. Yes? These, right, versus these. If these add up to be infinite, and those are bigger than those, then those will add up to be infinite as well. Okay, so we have to show that inequality. Let's plug it in. What is a sub n for us? It's n cubed over n to the fourth plus 1. Oh, wait, minus 1. And the question is that bigger than or equal to 1 over n? Cross multiply again. N to the fourth, bigger than or equal to n to the fourth minus 1. Subtract n to the fourth on both sides. 0 is greater than or equal to negative 1. Is that true? Yeah, that's true, right? 0 is bigger than negative 1. That means that it diverges. So therefore, by this comparison test, the original series we were looking at must do whatever the other one did.